Okay, our goal is to talk about Gauss's law right now. I'm letting this buffer here. Let me get my starting on page 33 in the workbook. Page 33, right? Whoops, right there. Okay, our goal is to talk about Sorry about that. All right, so before we talk about Gauss's law, I first need to talk about electric flux. Okay, electric flux is this mathematical quantity. Capital Phi subscript E, it's the integral of the electric field dotted with a differential area vector. Now, right now, this probably won't make a lot of sense, but I've got some simulations that will hopefully give you a feeling of what this means. Essentially, what you can do is you can take an electric field magnitude and this differential area and get the angle between them. More on that in a second. First, let's talk about the units of this quantity. That we can get without the simulation. This is newtons per coulomb times meters squared, right? In principle, I want you to think of the whoops, that's right here. Newton meters squared per coulomb. I want you to think of it as the number of electric field lines piercing a surface. So this isn't perfect, but it's a good way to think about it. And maybe right now I'll go to a simulation really quick. Let me show you what I mean. Oops, we want to go to this one. So right now, I put a whole bunch of point charges there. So the dark gray spheres are point charges. Now in this case, that yellow arrow, oops, let me get this. This is the electric field. And I know yellow on white isn't the best choice, but I'm trying to stick to our convention. And now I don't know if you can see this, but there's a small area here. That's dA, and I'm going to put a vector on that. The arrow here represents that dA vector. The size of the arrow is equal to the area of the square. The direction of the arrow is perpendicular to that square. So in this case, it turns out you could get a small amount of x times a small amount of y in the k-hat direction. So think that through. This has units of meters, this has units of meters, and this has units of meters squared. So this actually makes sense from a unit perspective. And so that's what a differential area vector is. You could just think of it as dx times dy, a small change in x, small change in y, or a tiny width and a tiny length, and then in the k-hat direction. Obviously, if I put my square up here instead, the area vector would be pointing upwards. So in this case, in the j-hat. So your area vectors could be dx dz in the j-hat. And that's what this one is, dx dz in the j-hat. So again, all this is it's an area with a direction. All right. Now, in this particular problem, let me clear out these annotations here. Whoops. I just want to point out, notice there's an angle between them here. And if you look down here at the bottom of the screen, the angle between these happens to be, 24.4 degrees. Let me go in and clean this up. All right. And now what I could do is I could actually pick different spots here. You could pick a different spot. How about this one? And now when we run this, notice here the electric field and the dA vector are closely aligned. There's only 12 degrees between them. All right. And so depending which spot you pick, if I pick a spot right in the middle, or very close to the middle, hopefully the angle is exceedingly small. Okay, only less than 5 degrees, right? So the dot product between those would effectively be 0.99 or higher, I believe. I'd have to punch it in my calculator, but you can see they're practically right on top of each other. All right. So that was supposed to give you a feeling for what this looks like. In theory, you could go to a surface, pick out every single point on the surface, get the size of the electric field from all the point charges. You could get the dA, which is probably going to be, like in this case, it's oftentimes going to be dx, dy, or dx, dz, or maybe it would be dy, dz. It's going to look something like that. Every shape is going to be a little bit different, but these are some examples, right? And if you got the area between these two, you could just punch in the numbers and do the integral. Piece of cake. Well, yeah, it's a little difficult. Now, in practice, what we really care about is going to be Gauss's law. So we learn about this electric flux concept because Gauss's law states electric flux through a closed surface is directly proportional to charge enclosed. So in this case, notice this integral is different than that integral. Here, the integral could be over any surface, one surface. This is over a closed surface, and it's equal to the charge enclosed divided by some constant. The constant happens to be this, which happens to be 1 over 4 pi k. So, and this is given to you on your exam equation sheet. It's just some constant. So for now, basically, you're supposed to use this interesting result that this electric flux is charge enclosed over a constant. Why do we care about this, right? This seems like just pure math, and it seems like it. I love it. But why should we care? In problems with exceptional symmetry, and I'll show you a few in just a second, Gauss's law will actually make electric field calculations simpler. And you may not see it right now, but I'll show you that in a second. And those results are used in our derivations of capacitance of various shaped metal plates. For example, 2 plates, and you could call that a parallel plate capacitor, or 2 cylinders. You could have a cylindrical capacitor or a spherical capacitor. So that's really the main reason I'm interested in this. That, and it's just really fun math. So that I just find it exciting. Turns out there are similar laws in gravitation and other things, but let's go on here. Let's get back to our simulation and look at something here. Oops, let me go here. All right, and so we've got this simulation here. Now, I just want to point out, maybe I'll rotate this so you can see it a little better, and I'm going to zoom out. I'm going to rotate just a little bit more. Okay, and so this, let me get let's use this. So there's various surfaces here. There's this one that I'm shading in pink, right? There's maybe one that I could shade in green. There's this surface here. So the front, the side, there's also the top. So this is a pretty complicated subject. Sorry, it's taking so many colors here. But obviously there's the back, the left side, the bottom. If we got the electric field dotted with dA, and remember in this problem here, whoops, the yellow line is the electric field. The red line, or the red arrow that's kind of covered up there, is dA. If we took the dot product between those arrows using this angle for every single point, and we did every single surface, all 6 of them, that would be a closed surface. The box is enclosed. My claim is that the integral of, whoops, let's get the marker here. Whoops, the integral of E dotted with dA, sorry, I'm slow. The integral of that should equal the amount of charge in the box. So the box is a closed, and that this implies this circle means over all surfaces. Sorry, I'm slow, but I just like the 3D visuals. So I apologize if this is painful for you to watch. Hopefully you could double speed it if it is. So if we go over all surfaces, the charge in the box over epsilon naught, and maybe this is helping, maybe not, but I'm trying to show you the difference between integrating over a single surface versus a closed surface. If you do that over all the surfaces, we've enclosed some of the charge, and you could go inside here, whoops, and you could count off the charges in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. And you could get the total charge in there. And what's weird is this integral turns out to be that amount of charge over epsilon naught. That's Gauss's law. That's what a closed surface is. Now, I mentioned for problems with exceptional symmetry, this can be useful. So let's look at some of those. In this case, here's a spherical problem, and I want to notice something special. I've drawn the electric field at many different points, and notice I only drew one Gaussian, one little surface here in red, but notice at any point on this sphere, the electric field is perpendicular to the surface. Interesting. Whoops. And at this one, for a cylinder, right? Now, this one's a little different. For most of the points, if we kind of ignore the ends, for these regions in here, approximately, we see that E, for the most part, is approximately perpendicular to the surface. And this is what I was talking about when I said ideal symmetry. If we use cases with ideal symmetry, like spherical surfaces around spheres or cylindrical surfaces around cylinders, most of the time the electric field is perpendicular for the sphere all of the time. Well, what is that going to do for us? Check this out. This is what I think is so really cool about this. Let me go over here. Let's go over here. In general, for any closed surface, the integral of E dot dA is equal to Q enclosed over epsilon naught. Sometimes I get lazy and I'll just call this Q in over epsilon naught, all right? Now, if E is perpendicular to the surface, E is parallel to dA. So to be clear, that means is parallel to. And this symbol means is perpendicular to. Just in case you don't know that. Sorry about that. So if E is perpendicular to the surface, E is parallel to dA. Remember, oops. If you have an arbitrary surface like this piece of paper, we say the area vector points perpendicular to it. So that's just a definition. Well, so if you roll this thing up into a cylinder, let's say, well, ignoring the end caps, which is what we're going to do, the region near the middle is all we really cared about for our cylinders. We see that the area vector is always perpendicular, and in the simulation you saw that the electric field vectors, until you get way down here, they're pretty much all perpendicular as well. All right? Why is that useful? Well, angle between E and dA is equal to 90 degrees. Cosine of 90 degrees is equal to 1. Oh, whoops. Ah, shoot, I just misspoke. It's 90 degrees to the surface. This is wrong. It's completely wrong. I'm so tired. 0 degrees. I don't know what I'm saying. I apologize. So I just misspoke. The point is they're parallel, it's perpendicular to the surface, parallel to each other. Whatever. Anyways, the electric field and dA will have an angle of 0 degrees between them because the electric field is pointing radially outwards, and so is the dA vector. When you have cosine of 0, that's what's equal to 1. And notice that makes this integral easier to do. We don't have to do that annoying dot product all the time. It just becomes E times dA. All right? Now, one extra caveat. If surface chosen wisely E, the electric field magnitude, is constant everywhere on the surface. Let me go back to our simulation. Okay. In this case, I generated this electric field by taking a whole bunch of point charges in there, right? When you look at it, notice the electric field arrows are all approximately the same size, no matter where they are. This is not true down here towards the end, right? Towards the end, there may be a little bit different size. They're a little bit different angle. But if we focus on the region near the middle of the cylinder, all of the electric field lines are perpendicular to the surface and about the same size. Same, with this one. Notice if we go the same distance from the point charge, all of the electric field arrows should be the same size. Why is this special? If you choose a spherical surface around a sphere or a cylindrical surface around a cylinder, all of the electric field arrows have the same size. That allows us to pop the electric field out. So look at this. Oops, let me get out of the way. If all the electric field arrows are the same size, this just becomes E times the integral of dA. And remember, what does that circle mean? That means integrate over all of the surface. So if it was a box, you did it over the top, the bottom, the left, the right, the front, the back. But if it was a sphere, that just means integrate over the entire surface. So essentially that becomes EA, where this is the area of my surface. This surface has a special name. It's called the Gaussian surface. All right? Hopefully that's still on there. Just barely. Okay. Now, to be clear, you may be saying, where does this surface come from? It comes from your mind. It's an imaginary surface that we draw around some charges. It does not exist. It only is in your mind. Okay? So the idea is, let's say you have some charges here. Maybe you have a cylinder of charge, right? You could draw an imaginary surface in your mind that matches the symmetry of the object. So for a cylindrical object, I think, well, why don't I draw a cylindrical surface? When I do this, I say, well, I know there's going to be some electric field arrows here. They start to angle over here. I know I'm drawing these a lot, but let me just get it done. All right. And so we see all these different electric field arrows. If I restrict myself to this center region here, I could say the area of that surface that I've drawn in my mind, the area of the cylindrical surface, I could plug into here. The electric field, I don't know, but I do know that this is equal to Q enclosed over epsilon naught. So if you draw the surface and you know the size of your surface, then you could predict the electric field at that surface. Notice the electric field will depend on the charge enclosed and the area of your surface, which is basically telling you something about the radius of your surface. And that is how we hope to use Gauss's law. I think that's a brief introduction. And then what we'll do is maybe we'll do some problems where we do these one-on-one. And like I said, it's been a long day. I'm already